Hello, fellow programmer. Today I want to share with you a simple problem that you can make money from. I'm talking about the Huawei Optimization Tournament. A quick disclaimer, I'm not sponsored by Huawei, neither by Algo Tester. Let's view this problem as a game. This is the data processing game. The rules are simple. There are data packets, and if you process a data packet at a given node, it goes into the next node. If you process a packet on the last node, you are considered done with this packet. Your objective is to process every packet in the last node. However, you don't have to do this one by one. Process the packet at node 0, it then forms a batch at node 1, and when you process the batch on node 1, it goes as a whole to node 2. The problem with batch processing is that there are multiple packet types, and you can only process one packet type at any given time in a single batch. In fact, there are three packet types. Each one has its own rules. Type 3, for instance, gets processed from 0 to 1, 1 to 8, 8 to 9, and from 9 it is considered done. On the other hand, type 2 is processed from 0 to 1, 1 to 2, and from 2 it jumps directly into 7, 7 to 8, from 8 to 9, and then it is considered done. Type 1 is special, it has a harder accelerator queue. When a packet gets processed in node 3, it goes into the hardware accelerator queue, and during this time you can asynchronously process other packets. Take packet 7, for instance, and process it into node 8. After some time, the packets on hardware accelerator get back into node 4. This is not the only occurrence for that, it happens again on node 5. The game starts with n packets to be processed. You can fetch packets at any point you want, but there is no guarantee you will receive any packets. Now you know the full rules of the game. Can you think of an algorithm that solves it? The simplest algorithm I can think of is to perform a linear search on every queue. Start on queue 3 and look for packets on node 0. If you don't find any, go to node 1. If you don't find any, go to node 8. If you find a packet, then process it, it goes to the next node, and your pointer gets back to the start of the queue. You do the same path once again, and you found it at 9, so you process it. Then you perform the same steps again, and this time you end up in queue 2. You could look into queue number 1 and number 2 only to find no packets to be processed, and this means it is time to fetch. And of course, if you find a batch, just process the whole batch. Recapping the algorithm, we will be processing queue 3 at first, and this happens because if you find a packet, you will process it, and then your pointer gets back to the start of queue 3, which means you will definitely get done with processing Q3 before you go into Q2. Then you go into Q2 and the same happens. Q1 is a little bit trickier because of hardware accelerator. However, the same applies to it, and if there's no more packets to be processed, you can proceed. Then you fetch more packets and run one more iteration of your loop. Is it a good algorithm? Well, I got 7th when submitted it. Can we make it even better? The answer is yes. You just have to like the video and subscribe to the channel. Suppose you found a batch of packets at node 0 for Q1 and also a batch of packets for node 9 on Q1. Our algorithm will process the batch of packets on node 0 first, but who said it is better to do this instead of processing the batch of packets on node 9 first? Q1 is complicated due to hardware accelerator. However, we could consider a batch of packets on node 7 instead of node 0 as this is much easier to analyze. Consider a few constants and functions. The total delay of the system at turn n is given by d of n. I don't know how the system got this delay, but it is there and we can do nothing about it. The time it takes for a batch to be processed from node x up to node y is given by a function t of xy. The time it takes to process a batch from node I to node I plus 1 is a constant given by the problem statement. Let's also consider a function s such that it evaluates the time cost of processing a batch from node x up until the last node. If you remember the problem statement, we already defined that nodes go up until 9, but now we are processing up until 10. 10 is just a padding that will be useful for these mathematical definitions. Define arbitrary batch sizes k and w. Our current algorithm will consider the updated delay after processing a batch of packets in node 7 up until node 9, and then from node 9 it forms a new batch and it is processed up until the end. Notice how every packet will be delayed, and so we must consider every time cost weighted by the amount of packets we have in the system. Another option would be to process the batch of packets on node 9 first, and then we proceed to process those on node 7. Let's expand one of those T functions so it is easier to simplify things when we compare those two algorithms. Now we can just subtract one from another and keep the one that has the smaller delay. Is it really better? Well, I got a few better scores after figuring it out and fixing some bugs, but I was running out of time and couldn't figure out a way of comparing those being processed at a node that comes before hardware accelerator and after hardware accelerator for Q1. I ended up 12 and had a lot of fun running through this challenge. I highly encourage you to check out the original problem statement as it gives a much more detailed explanation about the applications behind this problem. I hope you also had fun walking through this problem with me and hope to see you on the next video.